Hello and welcome to this video where today we're looking at the weak nuclear interaction. Now the weak interaction is a little bit strange in the sense that it isn't really a force between particles. What it actually does is it makes particles change from one type to another. And on the whole, the reason that it does this is because large particles with large amounts of mass and so therefore lots of large amounts of energy basically decay down into particles with a lesser amount of energy. So we've gone from a high energy state down to a lower energy state, and so that's energetically more favorable. So in general, that's what the weak interaction does. It makes one type of particle change into another type of particle. Now it acts on both quarks and leptons, so there are examples of decays both in terms of particles made up of quarks and also the lepton particles. We're going to start off by looking at one interaction that is actually really well known. So we're going to look at the decay of the neutron, and actually in terms of beta decay. So basically what happens, as you will remember from GCSE, here we've got a neutron and it spontaneously decays via the weak interaction to a proton plus an electron. However, if we then have a look at all of our conservation laws, if you look at baryon number is not a problem, because that's a baryon and that's a baryon and that isn't a baryon, so therefore that's fine. Charge is also fine because we started off with a neutral particle and all together we finished up with a neutral particle. However, in terms of lepton number, there's no leptons here, but there is here, so we need to balance it out. So we actually need to add in an extra particle, so we're going to add in order to balance the lepton number, we're going to add in an anti-electron neutrino. So that's actually the full decay for the neutron. So at GCSE you learnt just the neutron goes to a proton plus an electron. Now the full equation is a neutron goes to a proton plus an electron plus an anti-neutrino, and it's an anti-electron neutrino, not a muon or a tau neutrino. Now what's basically happening to change your, if you look on a quark level, is you're starting off with your neutron, which has got a quark structure of up, down, down. And basically what's happening is one of the down quarks is changing to an up quark. So for example, this down quark is changing to this up quark over here. So your weak interaction is basically making this, it leaves these two quarks alone. This down quark becomes an up quark, and in order to conserve charge and baryon number and lepton number and so on, it also then emits your electron and your electron antineutrino. So you can write this in a number of ways. So you could write out your full equation in terms of, for example, neutron goes to proton plus electron antineutrino, like that. You could, for example, just do it in terms of quarks. So you could have your down quark becoming a up quark and also emitting your electron and your electron antineutrino, like that. You could do it in terms of, for example, nuclei. So we could have, for example, a boron nucleus, which becomes a carbon nucleus, for example. So what's happened is basically this neutron here has turned into this proton. So that's happened, and again you get an obviously you get an electron and electron antineutrino being emitted, because that's what happens in beta decay. So we could write this as, for example, you've got boron and we've got 1, 2, 3, 4, 5 protons down here, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got a boron nucleus, and that's gone to a carbon nucleus, and if we look at that, it's got the same number of nucleons altogether, so they're the same. However, this neutron has become a proton, so this has changed and has become a 6, and that's the reason that this is no longer boron, it's carbon now. And again you get your electron and your electron antineutrino, like that. So this is how you would write beta minus decay in terms of the nuclei. So basically what's happening is that the proton number actually increases by 1, but the nucleon number actually stays the same, because if we put the numbers on here, This hasn't got any nucleons, but it has a charge of -1. And really what the numbers at the bottom are telling you are the charges rather than the actual number of protons. And this neutrino has got a nucleon number of 0 and it's not charged. So it's got a charge of 0 at the bottom. So basically we can make sure that all these things add up. So 13 goes to obviously 13 plus 0 and 0, which is fine. 5 goes to 6 minus 1, which again is fine. So this is your kind of bog standard beta minus decay equation. But what's really happening is this neutron is becoming a proton, and at the quark level what's happening is your down quark is actually turning into an up quark. But in all cases you get an electron and an anti-electron neutrino being emitted. Now we can draw some pictures of basically what's going on, and what we're going to do is we're going to have a look at these things. So we saw a little bit about Feynman diagrams before. We're going to look at them in a little bit more detail. Okay, so this time what we've done is we're looking at a different equation. So what we're going to do is we're going to look at beta plus decay, and we're going to get all of our rules for beta plus decay Feynman diagrams from this picture. So basically what happens with this is a proton becomes a neutron and a positron this time, and this time an electron neutrino. So the equation looks similar, but it's completely different, but everything works. So the charge is still conserved, baryon number is still conserved, lepton number is still conserved, so that's fine. So what we do is we draw the particle. So basically we draw the particle that is we start off with at the bottom of our diagram, because if you remember, time is going upwards. So time is going up here, like that. And so before our interaction, so this is anything below this dotted line, for example, is below our interaction. Anything above the line is what we get afterwards. So we start off just with a proton, just this proton here, and it becomes our neutron. Now in order to do that, it has to decay, and basically what happens is it decays through the weak interaction. And as we saw in the previous video, the particle that mediates the weak interaction is the W particle. Now this W has got a charge. In fact, all W's have a charge, and they're either positive or negative. And we have to decide often whether or not this is a positive W particle or a negative one. And the way we do that is we look at each of these things here are called vertices. So basically we look at where particles are splitting up. So if we look at this vertex here, for example, like that, we've got a W particle there, we've got a proton here, and we've got a neutron here. This proton's coming in like this, and these two particles are going away. So if we think about the charge going in, the charge going in is +1. So we need to end up with a charge of +1 when we finish. Now this neutron's got a charge of 0, so our proton has a charge of +1. Neutron's got a charge of 0, so to balance this, our W particle must have a charge of +1 as well. So therefore we can put a plus on here like this. Okay, and then the W particle comes along and it doesn't live for very long, and basically it decays, and it decays into our electron and our neutrino. And again, if we look at this particular vertex, then we've got our positive W particle coming along. It's decayed to our neutrino and also this positron. And again, you can make sure that the charges actually follow through. So we started off with our W particle, which has got a charge of +1. It's gone to our neutrino, which has got a charge of 0, and it's gone to the positron, which has obviously got a charge of +1. So again, everything balances. So if you want to work out the charge of these particles, look at one of these kind of corners and look at what's coming in and what's going out, and what again, charge has to be conserved in this part. So you can basically make sure that all of the charges match up, and you can then decide what charge this W particle's got. Again, if we want to do this on a quark level, you can see that basically what's happening this time is that up quark is changing to a down quark, and then the rest of the Feynman diagram looks exactly the same. So that's your Feynman diagram for beta plus decay. We'll just complete this, because what we'll do is we'll just make sure that we can actually now draw, we'll go back to the beta minus decay, and we'll make sure that we can do exactly the same thing. So let's put a line down there. So let's have a look at beta minus decay again. So we're going to go back, and if you remember, beta minus is when a neutron becomes a proton and an electron and an electron and neutrino. So let's try and draw this thing from scratch now. So if we look at this, the first line is whatever particle we're starting off with, this one here. So we would draw a line like that. So that's our neutron. We'll label it with an N. It then converts into a proton, and this is our proton here. Now the important thing to realize here is that our baryons, the things made of quarks, are staying on the same side. So this electron doesn't suddenly appear over here or anything. The quarks, if you like, are continuing on the same line. It's just that only one of them's changed. So our neutron's come along there, proton's gone up here, and this thing then there's now a W particle, and we need to decide what charge this has got. And then when it comes off here like this, we get two particles. You've got your electron and you've got your antineutrino. So let's have a look at this part here. So you've got your neutron, which is coming along, and obviously neutron's got zero charge. That's gone to a proton here, which has got a positive charge, plus our W particle here. And remember, we're only looking at this corner, we're ignoring this one altogether. So this particle here, in order to make this thing balance, must have a minus charge. So this is a W minus particle. So it's basically the opposite of this thing. So that's basically what's going on. I suppose the final thing to say about these types of decay is that sometimes people then draw on the quarks that aren't changed. So for example, this one, where our neutron becomes a proton. So if you remember, the quark structure for a neutron is up, down, down, and it's gone this, so that's your up, down, down there, and here it's gone to up, down, up. You could also, for example, so if we drew the Feynman diagram for, in terms of quarks for this thing, the down quark is becoming an up quark like that, and then the rest of the diagram is basically the same. So you've got W minus, electron, and anti-electron neutrino. And you could then draw your other two quarks. So you could draw this down quark, which is staying the same, down, down, and your other quark, which is staying the same, which is your other up quark, like that. So this up quark stays the same, doesn't do anything. This down quark stays the same, doesn't do anything. But this down quark changes into an up quark. What's really important in any exam question is you check to look whether or not the exam question's asking for things in terms of protons and neutrons, or whether it's asking for things in terms of quarks. So we can go a little bit quicker now, because we can have a look at this. So this is electron capture, and basically what happens with electron capture is you've got your nucleus, and it's potentially got too many protons in it, and your electrons are orbiting around the outside, and one of them might, for example, one of these electrons might get a bit close to this proton, and essentially the proton grabs it, and it converts it into a neutron. So if you write the equation down, you've basically got a proton plus an electron goes to a neutron plus your electron neutrino again, like that. And again, if you think about your lepton numbers and charge, then this thing's absolutely fine. Your Feynman diagram looks like that, and so again, this is just something that you need to learn, really. So that's electron capture incredibly quickly. And then finally, you can have neutron-neutrino interactions where, again, your neutron and your neutrino are interacting, again via the weak interaction, and your neutron becomes a proton. Again, all of the quarks stay on this side. When the neutron interacts with this neutrino that just comes from the environment, it changes the neutron into a proton, and an electron is emitted from your nucleus. So they're basically the different Feynman diagrams that you really have to know either how to draw, or how to actually or basically how to take an equation and draw, or alternatively just draw from scratch, or alternatively again decide what particles go where, basically, and what the charge of this thing is. A very common question is working out what the charge of this W particle is. Now there's a fairly straightforward way of actually remembering these. So if we go back to, let's get rid of this. If we go back to this particular equation that we've got over here, so we'll move this over here. We've got this is our beta minus decay, because a beta particle is basically an electron. So beta minus basically means it emits an electron. Beta plus means it emits a positron. If we look at this, this is the only equation we need to remember, because we can get every other equation from it. So let's imagine that instead of a neutron changing into a proton, we've got a situation where a proton changes to a neutron, but we can't remember the equation. Well, we can get it from this, because what we really want in the end is we want an equation where a proton changes to a neutron plus other things. Now these things work exactly the same as normal type of mathematical equations. So with a mathematical equation, what you often do is, if we work down here, if you've got something, for example, like y equals x plus 1, pen x plus 1, like that. If you want to make x the subject of this, what you really do is you say y minus 1. So you take 1 from both sides basically, equals x plus 1 minus 1. And your plus 1 and your minus 1 cancel each other out to become 0. And so essentially what has happened is the 1's appeared on this side, but with a minus sign. You can do the same with these things. So if I add, for example, a normal electron neutrino to both sides, the electron neutrino will stay on this side, but the electron neutrino on this side will cancel with its antiparticle. So basically you've cancelled these two things out. So you can move them from one side to another, not by changing the sign, but basically by changing the type of particle. So we'll do it step by step just so you can see. So I want to get, in the end, I want to make P the proton the subject of this. So I'll get rid of the neutrino first, just like I said. So what I'm going to do that, I'm going to do this. So I've got my proton, and I've left a gap here for a reason, as you'll see in a sec. Electron plus electron antineutrino. So if I add a normal electron neutrino to this, these things basically cancel each other out. So I've got an antiparticle and a particle. But if I add an electron neutrino to this side, I must do it to this side. So because it's an equation. So I've got that. These two things cancel each other out, so basically disappear. So if I tidy this up, I've got neutron plus electron neutrino goes to a proton plus an electron. So I'm halfway there. But actually, this was our last Feynman diagram that we had a look at. So this was actually our neutron-neutrino interaction, where a neutron and a neutrino interact to make a proton and electron. But I don't want that one. I want this one. So I want proton goes to neutron plus something. So I need to get rid of this electron. So what I'm going to do with there, I've got my neutron plus my electron goes to my proton plus E minus. To get rid of the E minus, I'm going to add the antiparticle of this thing, in other words, the positron, so the E plus bit. But if I do it to this side, I also have to do it to this side, like that. And now I've got this and this which cancel each other out, so they've basically disappeared and to 0, and so I've just got proton on its own. So if I rewrite this the opposite way around now, I've got this P goes to my neutron there, plus, and we'll write it in the standard way, this positron plus this neutrino here, this electron neutrino, like that. So I can get any of my equations that I want for any Feynman diagram that I need to remember from this one equation. So if I take this one equation, I can basically rearrange it into any one I want really. I can put I can change my neutrino to the opposite side to get neutron neutrino. I can basically have my electron capture, which is my proton and my electron, basically by, again, if I take the neutrino to the opposite side and then just switch the sides round, that's the same thing. So from this one equation I can get anything that I want really. So the final thing I need to have a look at is basically an extension of the conservation laws. So because as well as lepton number, as in whole lepton numbers, individual lepton numbers are also conserved. So I've got two interactions here and I want to know basically what's going to happen. So one of these can happen, one of these can't, and I want to know which one can. So if I do my charge, for example, charge for both of them is fine. So charge I've got -1 goes to -1 plus 0, oops, plus 0 like that. And again, if I do the same thing here, I'll get exactly the same thing. So charge works, baryon number will work because none of them are baryons. So basically 0 goes to 0 plus 0 plus 0, so that's fine. And if I look at lepton number, then lepton number, this is a lepton, so that's +1 goes to, this is a lepton, +1. This is a lepton, +1. This is an anti-lepton, so -1, +1. So this side is 1, this total side is 1, so that works as well. And I could do the same on this side, so basically you'll get exactly the same equation, give or take. So the lepton number for this one is +1 goes to, again, that's a lepton, so +1 plus, so plus a -1 because that's an anti-lepton plus 1 because that's a lepton. Again, I've got +1, -1, +1, so that's 1 and that's 1, so again, that should work. However, I know for a fact one of them doesn't. So what I can do is I can split it down into this. So I can split it down into electron lepton number and muon lepton number. And what I do is in exactly here, I said that anything that was a lepton is +1 and anything that isn't a lepton is a 0. I can do the same thing. So anything that isn't an electron type lepton is a 0, and anything that is a lepton type particle, that an electron lepton type particle is a +1, and if it's an antiparticle of it, then it's a -1. So let me show you. So this is a muon. This isn't an electron type particle, so actually that's a 0. That goes to this. Well, this is an electron type particle, and it's a particle, so it's a +1. This is an electron type particle, and it's a proper part. It's a particle. It's not an antiparticle, so that's a +1. This is a muon type particle, so isn't an electron type particle, so that's a 0. So I've gone 0 goes to 1 + 1, so 2. In other words, that one doesn't work. So let's try this one. My electron lepton number. So again, that's not an electron type particle. So 0 goes to this one is. This one's an electron antiparticle. So that gets a -1. This one isn't a electron lepton particle, so that's a 0 because it's a muon type particle. So I've got 0 goes to 0, so that works. I can also do the same with my muon number, so muon lepton number. Well, this is a muon, but we know for a fact this doesn't work because of this thing, but let's just check and show it doesn't work. So this is a muon, so it's a normal muon particle, so that's +1 goes to 2 electron type particles, 0 plus 0. And then this is an anti-muon particle, so that would be a -1. So we've got +1 goes to -1, so again, doesn't work. But on this side, hopefully this will work. So our muon lepton number, we've got +1 goes to, again, 2 electron type particles, like that. And then a muon particle, and it's a normal particle, so I've got 1 goes to 1, so that's fine. So that is how you can use electron and muon lepton numbers, not just leptons as a lump, if you like, as a whole thing. You can use individual electron and muon type numbers to decide again whether or not particle interactions work. So that's basically what the weak force does. If we go back to the beginning, then just to kind of summarize, this is basically what happens. You're expected to know, for example, that neutrons decay into protons. All of the Feynman diagrams here, you're expected to be able to draw and also write the equations out for them. And the very final thing that just to give you some advice, strangeness doesn't have to be conserved in the weak interaction. So we saw in a previous video that for the strong force it does. Strangeness has to be conserved, whereas in the weak interaction it doesn't. So if you have an interaction where everything's conserved and everything's fine, but the strangeness isn't conserved, then it has to be a weak interaction. Another kind of tip is if you have a neutrino in an interaction like this, for example, this has to be a weak interaction. Neutrinos only interact via the gravitational interaction, and we're not bothered about that one because it's so weak, and the weak interaction. So if you see a neutrino in something, then it's a weak interaction particle. Sorry, it's a weak interaction. And then the final thing to say is that in the end, this weak interaction works on every single thing. We know it works on leptons, and it works on quarks. In the end, every single thing that's made of quarks in the end becomes a proton. The proton is the only stable baryon that there is. And also, the electron is also the only stable lepton with mass as well. So in the end, everything would be, if everything was free, every single baryon would become a proton, and every single lepton with mass would become an electron. So that's basically the weak interaction. You need to be able to write all of these equations down, draw all of the Feynman diagrams that I've been through, and also know that the proton is the only stable baryon, know that the electron is the only stable lepton that's got mass, and then finally, really, you need to be able to check, for example, that interactions happen in terms of the electron and the muon lepton number, as well as the lepton number as a whole. Okay, that's the weak nuclear interaction, and thank you very much for watching. I'll see you again soon.